there's a variety of ways to approach this problem, but I think the most straightforward is with what you know now. Basically working from simply the tool you have here, turn this back into an exponential equation. If we do the little circular motion here, we'll have this set up. We'll have 16 to the 1/4 is equal to the square root of x minus 1. Now at this point you should realize that 16 to the 1/4 is the same thing as the 4th root of 16, which is 2. 2 times 2 times 2 times 2 equals 16. So this becomes simply 2 is equal to the square root of x minus 1. And if we square both sides, we get 4 is equal to x minus 1. So x must therefore be 5. Because 5 minus 1 is 4. We can check. 5 minus 1 is 4. Square root of 4 is 2. 16 to the 1/4 does indeed equal to 2. So it works. One more. Now, this is related to today's lesson a bit here. It would sure be nice if I could walk to my calculator and put log base 3 at the square root of 27 to get an answer. But you see, I do have some logs in the calculator right here and right here. This is log base 10 and log base e. Don't have a log base 3 anywhere on here. Okay, so I can't do that. We can, but we're not ready yet. So what I'll do here is I'll say, well, this value is going to be equal to some value of x, so I'll just call it x. This gives me a way to write 3 raised to something has to equal the square root of 27. 3 raised to the x is equal to the square root of 27. Of course, the square root of 27 can be written as recall from your intermediate algebra class that when you when you have a fraction, this is the root and this is the exponent. So I basically just took it one step backwards and said, well, if I'm taking the square root of 3 cubed, I needed a base of 3 to match up with this base of 3, so I had to write it in terms of 3, and I changed it from a radical to a rational exponent. And then since the bases are the same, I can drop that, and x must be 3 halves. You guys okay with that? Awfully quiet. Thank you. We got a camera on.
Wouldn't it be wrong if you did 27 to the 1/2?
It would not be wrong, except for 27 to the 1/2 would not allow me to drop the bases. Because the only way I can solve for x is if I have the exact same base of 3 here to get rid of it. Does that make sense? Because x is equal to 3 times. Okay, it brings up an interesting point. These types of equations, for example, let's see. 3 to the x is equal to 9. What does x equal to? What is it equal to? What does x equal to? 2. Is everybody okay with that? 3 squared is 9. How about 3 to the x equals to 10? What does x equal to?
2 plus 1.
That would be 3. And 3 to the 3 is 27, not 10.
3. 3 squared plus 1.
Okay, well I'll take that, but that still doesn't tell me what x is. Point I'm trying to make. Put a 9 here, we can do the following. Put a 10 here, we got a big problem, right? Now you do know this, that 3 to the 2nd is 9, and 3 to the 3rd is equal to 27, and that if I'm looking for 3 to the x equals 10, that falls somewhere in here, really close to this one, so it's probably 2.1 as a guess, strictly a guess. We need to find out a little bit more than a guess, right? So that brings up today's lesson. Let me go ahead and pass out the first worksheet.
Kind of good thing is that the good thing about this class is that the first class of the day, you seem to go over everything, so you're more, I don't know, you know what
Prepared.
you're going for. You're more prepared, organized.
1, 2, 3. There you go. Here. Oh, here we go. Before I can show you how to do this, there's one property that we need to know about logs. It's one of the most useful properties. And it's written right here. I'll circle it in blue for a second. Let me rewrite it here. Okay, log of any base A, of course, A still has to satisfy the fact that A is bigger than 0 and not equal to 1. Strictly bigger than 0, not equal to 1. If you take a log base A of x raised to any power, you can take the exponent and move it out front and use multiplication. This is one of the nice things about logs because it gives you a method or a way, if you will, to knock the exponents down into a more manageable position. We can solve for things when you multiply. It's hard to solve for things when you raise them to a power, right? When you multiply, you can divide the other stuff away. For example, number 1 on the worksheet. 3 to the b is equal to 17. Now, we've seen equations like this before, where we put the same base on either side. For example, had this said 3 to the b equals to 27, well, then b would be equal to 3. But it says 17 this time. There's a process here, but before we do that, we could maybe make a guess. We know that 3 squared is 9, and we know 3 cubed equals to, well, 27. So what do you think? 17 somewhere in here, so this should be 2 point something. 2.5 maybe, right in half? That's really just a guess, okay? Let's see how you might do this for real. What I want to do is I want to take the log of both sides of this equation. So I'm going to write log base A of 3b is equal to log base A of 17. I can take the log of both sides of the equation and maintain equality, right? If I have two things that are equal, then their logs of the same base should also be equal. And this may not seem to help me at first, except that there's a really good choice for A here. What is it? What's a good choice for A? 3. Well, no, 3 is not a good choice. I see why you might want to choose 3, because then you could write B. Actually, 3 would be a pretty good choice in that respect. That's a good observation. If I could put a 3 here, I could then say that B is equal to log base 3 of 17. If I turn this back into an exponential equation, I'm right back to where I started. 3 to the B equals 17. So although it works good on this side, it doesn't work so good on the other side. So nice thought, but what's a better choice for A?
17.
17 won't get me anywhere either. What's a good choice for A? Actually, there's two good choices. Who said 10? It is 10. Why is 10 a good choice? Because you have a button. That's exactly right. You have a button right here that says log base 10 is the only one you have a button for. Well, that and log base E, which is the one right below it. So since we know that, so let's go ahead and take log base 10 of both sides. Now, using this rule right above it, when we have an exponent, we can move it out front. I can get B times log base 10, and you don't really need to write the 10. It's understood. Remember, log base 10 is just simply written as log. Of 3 is equal to log base 10 of 17. What is the operation between here? So how do I undo that? Divide by log base 10 of 3. And I'm going to stop writing log base 10 of 3, or 10 after this. These cancel away, and you get